Welcome to Reliability Matters, a podcast for the electronic assembly industry. Each episode covers topics related to reliability, best practices, and environmentally responsible assembly techniques, with insights from experts across the electronic assembly industry. Now, here's your host, Mike Konrad.
Welcome to another episode of Reliability Matters. This is episode 16. Today I'm coming to you from Baltimore, Maryland. I traveled to Maryland for the IPC High Reliability Conference, where I was a speaker. That was a terrific event. Experts in cleaning, materials, microvias, and so much more presented 3 days of valuable and relevant content. This is an annual event. If you're in the electronic assembly industry, I highly recommend this conference. In a couple of days, I'll be teaching a workshop in Rockville, Maryland on the subject of reliability of circuit assemblies. The following day, I'll travel to Raleigh, North Carolina, and teach the same workshop. I'll do the same thing next month in Melbourne and Tampa, Florida. If there's ever a desire to learn where I'll be next, either at a live event or a live webinar, just check out the events section of aqueoustech.com, or follow me on Twitter @aqueoustech, or search for me on LinkedIn, Mike Konrad. That's Konrad with a K. Today, I'm bringing back one of our more popular presentations, SMT Wars, Lessons Learned from a Contract Manufacturer and Their Customer Who Sued Them. A few years ago, I was hired to be an expert witness in a civil litigation matter. An OEM was suing their contract manufacturer for essentially doing exactly what they were asked to do. This OEM had a novel idea for a new product. They designed the product and sought out a contract manufacturer to build it. The OEM produced a statement of work and provided detailed assembly instructions, quality control procedures, and more. Unfortunately, what the OEM didn't realize was much of the assembly instructions provided to the contract manufacturer didn't follow best practices. This and other factors led the product to ultimately fail in the field, resulting in a recall of tens of thousands of units. The OEM believed the contract manufacturer should have known better than to follow their instructions and held them responsible. The contract manufacturer indicated they were just following their customer's instructions. The result was a multi-million-dollar lawsuit. There are so many lessons with this event. What to do when your customer asks for something that will lead to failures, what to do when your customer places shipments in front of quality, what to do when asked to skip important process steps, etc. When and where does ownership over reliability pass? Did the OEM get what they paid for and nothing more? Did the contract manufacturer put profits in front of quality, either knowingly or unknowingly? Were fear-based decisions made by both sides? Well, listen and decide for yourself. I like to title my presentation chapters a little bit uniquely. So we start off with what I do, which no one really cares what I do, but it's relevant to the story in this case. Then there's a section that I call "This is going to be interesting." There's another section called "Low Battery," and then "Electrochemical Migration Crime Scene Investigation," ECM CSI. And then another section called "We Don't Have Time to Do It Right, but that's okay, we'll just do it over." And we'll get into some technical takeaways, and of course, we always end everything with the moral of the story. So let's get this started. This is my world, and this is probably your world as well. I work in the electronic assembly equipment manufacturing industry, so I wake up to circuit boards in my head, and I go to sleep with circuit boards in my head, much like probably most of you. My world takes it to a little bit of an extreme. My job is to prevent stuff like this from happening. And if I could quote our friend Benjamin Franklin, "An ounce of prevention is worth a pound of cure." And that's what this particular presentation is all about. The company that I'm going to talk about probably would have done well by heeding this advice, which they didn't do. We're going to talk today about electrochemical migration and its different manifestations. This is what a board looks like that's been a victim of ECM, electrical chemical migration. This is one of the dramatic consequences of a board that's suffering electrochemical migration in its extreme form. And this is one of the results of a circuit board that can catch fire. The product that the circuit board is in can then catch fire. And it's a very dramatic, unfortunate, and totally preventable event. If all you have is a hammer, everything looks like a nail. And I'm sure most of you can identify with that particular statement. Well, in my world, and maybe yours too, I kind of see the world as one giant circuit assembly. Working in this industry, you just kind of find the circuit assemblies in pretty much every product that you own. And the problem, particularly in my industry, I specialize in electrochemical migration prevention and how to prevent dendritic growth and shorts and parasitic leakage and blah, 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 blah. And when I go to a cocktail party, what I dread the most is when people say, "What do you do?" Because what I do is not very exciting. In fact, the more I explain what I do, the more results like this I see. And maybe your case isn't quite as bad because you probably do things far more interesting than what we do here. However, this is kind of the consequence of the career path that I've chosen. So you can imagine one day I get a phone call from a lawyer, and the lawyer starts mentioning terms like contamination, electrochemical migration, conductive anodic filament failures, fire, lawsuits, and it's not often someone calls me and wants to talk about that stuff. And that was kind of music to my ears. And so I ended up being hired by this law firm to serve as an expert witness in a civil litigation matter between a contract manufacturer and their customer, which was an OEM. So I'm going to tell that story. Of course, I'm under a non-disclosure agreement, so I can't give away too much specific information. So the information that we're going to talk about will purposely be just a little bit fuzzy to protect the guilty and the innocent alike. So there was an inventor, and this inventor was quite a smart guy, and he came up with a pretty novel idea within his field. And like a lot of inventors, he had the intellectual knowledge to produce this part. The problem is he lacked the capital, and without the capital, he lacked the logistics, the factory to get this product made. And that's a pretty typical problem when people come up with bright ideas. However, he followed the path like a lot of inventors do. He got money through venture capitalist funding, and that allowed him to hire a contract manufacturer to produce the goods. So all was well. Their product, I can't say specifically what their product was, but I can describe how it was built. And basically, it was a small circuit assembly, a multi-layer board circuit assembly that was potted and operated off a battery. It was a 10-year battery. That potted part, which was not connected to an external power source, only ran on the battery, was then buried in the ground, and it would send data to a nearby receiver mounted on a pole near where the potted product was buried. And the potted product would communicate through radio frequency to the receiver. And that was the nature of how this product worked. So here's their process in a simple way, in simple terms. They specified, and I quote, down and dirty FR4 laminate. The down and dirty comment, which is not an IPC slash sheet, would come to haunt them later. But anyway, they specified to the contract manufacturer, you guys get the board made. Here's the design of the board. Here's all the files. You guys get it made and just get down and dirty FR4. They reflowed this particular assembly with water-soluble paste, which is certainly no sin. They cleaned it with just water because it was a water-soluble flux. It came off with just water, so they didn't need a chemical additive. They hand soldered after everything was assembled. They hand soldered a kind of a large mass through-hole device onto this board, and they didn't want to clean it again, so they used no clean flux. Again, there's no sin in that. And then they had no bake-out process, which will be relevant in a little bit, and the entire product was potted in silicone. They had no knowledge of ECM-related failure mechanisms. During depositions, they were asked about ECM and dendritic growth and conductive anodic filament issues, and that was all acronyms that were unknown to them. So what happened? What happened after they started producing boards? Well, they had electrochemical migration issues, and that resulted symptomatically in low battery. Their 10-year batteries were drained after about 3 months of use, after they were buried in the ground. They had dendritic growth on the surface of the assembly, and they had some electrical shorts on the assembly as a result of that dendritic growth. They also had a pretty substantial corrosion issue on the surface of the assembly in a potted environment, by the way. So what are the primary causes of electrochemical migration? Well, the two primary causes that can be controlled are contamination and moisture. Of course, it takes electrical current, a conductive corrosive residue, and moisture to form ECM. And the two areas that they had control over were, of course, contamination and moisture. ECM manifested itself in this particular example in two ways. They experienced conductive anodic filament failure, or CAF, and they experienced dendritic growth. So let's talk about CAF first. I like to call it CAF with two F's, because usually conductive anodic filament, if present on a board, also results in some type of failure. So it's kind of CAFF, conductive anodic filament failure. And it's important to note, we're a cleaning company, but cleaning isn't the fix for CAF. There's no way you can clean yourself out of a CAF issue. But a CAF is extremely easy to avoid, but cleaning is not going to be the answer in this case. So just by way of context, CAF was first reported in 1976, I imagine by this guy, from Bell Labs. They were the first ones to report it. And I like to define CAF as subterranean electrochemical migration, subterranean ECM. So let's look at, in a very fourth grade animation way, let's look at how circuit assemblies are or circuit boards are manufactured or fabricated. In this case, there was a multi-layer board, which is true for most assemblies, and they took the various levels of laminate and prepegs and all the different layers of a board, and of course they pushed them together under a great amount of pressure to form a single laminate, which consists of several laminate layers. And then after the various levels of laminate are pressed together under a great deal of pressure, there are the need to drill holes for through holes and for vias. So there's a drilling process that's used to drill through the laminate, very specific areas where the through holes and vias are going to be. And during the drilling process, it's not uncommon for microcracks to form. Microcracks can form due to damage to the laminate caused by drilling. Could be dull drills, too much pressure. It could be inadequate resin flow or dry weave in the actual laminate. And sometimes these cracks can form after the drilling process due to multiple thermal excursions. If a board goes through several reflow processes, for example, that can exacerbate the microcracks that are present. So now we've formed these little microcracks, which on their own are no big deal. They're fairly normal, and one would never know they're there unless other things happen. So after the holes are drilled, the next process is to plate the holes. So they usually copper plate them or other materials, generally copper. And part of the plating process involves plating solution, and this corrosive plating solution goes down the hole and allows the plating process to occur. And sometimes the plating solution, if there's microcracks present, leach into the microcracks. And that can be problematic, because if plating solution leaches into the microcrack, and if there's moisture and electrical current present, we could actually start growing basically dendrites, only to grow the opposite direction of a surface dendrite. So the next thing that happens after the plating process is through and the boards are completely fabricated as they're shipped out to the assembler, and then the assembler stuffs components on them and through them. And in this case, there were some axial leaded devices that were put in. And when the switch got turned on, the electrical current started flowing, and we had a space between a cathode and an anode, and there was a little microcrack that kind of filled in the gap between those spaces, and the microcracks were filled with conductive solution, and what happened was they formed a conductive filament, CAF, conductive anodic filament. And in the case of this particular contract manufacturer, this particular end user, the boards failed due to the unintended conductivity between anodes and cathodes. That results typically in a loss of resistivity, and that particularly in this case resulted in a drained battery. So the batteries, instead of lasting 10 years, lasted about 3 to 6 months. And then the parts that were dug into the ground had to be dug up, and batteries replaced and boards replaced, etc. And of course, CAF generally doesn't result in a fire. Usually the filaments are so thin they can't carry enough current to actually create a fire. They can smoke a little bit, but generally they just cause a loss of resistivity, an increase in conductivity, which can cause the instruments to fail, not be able to be calibrated, battery drains, things like that. Cleaning is not the way out of it because the problem is not on the surface. The problem is within the inner layers of the board. So cleaning on the surface is not going to do anything. So let's look at their process. Again, they specified down and dirty FR4. They reflowed with water-soluble paste. They cleaned with water, no chemicals. They hand soldered a through-hole device with no clean flux. They had no bake out. They potted the entire assembly, and they had no knowledge of specific ECM-related failure mechanisms. So what part of their process contributed to CAF? Well, these areas did. Specific down and dirty FR4 was selected. There are materials that, other FR4 type materials that are more CAF resistant. They didn't choose those, so that contributed to CAF. They had no bake out process. If they had simply removed the moisture, that would have prevented CAF. And they had no knowledge of specific ECM-related failure mechanisms, including CAF. These are the contributions that were made in the design and assembly of the boards that contributed to the formation of CAF. So let's look at the CAF ingredient list. What's required? Well, CAF is affected by design, how close anodes and cathodes are to each other. The amount of bias, the amount of voltage on the board affects CAF. The presence of conductive corrosive material, in this case plating solutions within the inner layers of the board, affects CAF. The electrical current, as I mentioned earlier, is required. No electrical current, no CAF. It requires a pathway. The microcracks in this case comprise the pathway, and it requires moisture. No moisture, no CAF, no pathway, no CAF, no electrical current, no CAF, no conductive corrosive material, no CAF, and a proper design, more than likely, no CAF. So the areas within their control, of course, were design, pathway, and moisture. They didn't have any knowledge of CAF. They'd never heard of it before, which is not unusual. CAF is not widely known. Big problem, but not widely known. And there is a IPC test method to test for the possibility of CAF, and that's IPC J Standard 001 test method 650 2.6.25. I'll let you all look that up. But there's a whole test protocol on CAF, which would be helpful to know if there's a concern that CAF could be possible in your assemblies. There's also aftermarket third-party companies, products that will test for CAF. None of these are anything to do with us, by the way, but DFR Solutions has a CAF test. Gen 3 Systems has a machine that can test for CAF. There are design considerations to avoid CAF, particularly with the laminate materials that the board's made out of. There are brands of laminates that are purported to be CAF resistant, and those certainly would reduce the likelihood of CAF because of how the laminate is constructed. The chance of forming microcracks are reduced or eliminated with these CAF resistant materials. They also had no bakeout. That was a significant part, probably the most significant part of their calf issue, was they had no bakeout. Now, keep in mind, the boards were fabricated in China, which is no big deal. That's quite common these days. They were put on a container ship where they spent several days at sea and rail car, I would assume, and then ended up in a factory. There was no evidence of first in, first out or inventory control. And there was no evidence that boards were kept in any type of dry box or any kind of humidity controlled environment. So moisture was allowed to pick up onto the boards during the fabrication process and during the shipping and storage processes. So no bakeout was certainly a major contributor because it requires moisture. No moisture, no calf. They also had a dendritic growth issue, and the basic difference between dendritic growth as classically defined and calf is where it's located and the direction, whether it goes from anode to cathode or cathode to anode. But dendritic growth is on the surface of the assembly, and dendritic growth looks like, more typically, the picture on the left, that looks like a tree branch. And dendrite comes from the Greek word dendron, which means tree. The picture in the middle shows kind of a white haze. That's actually dendritic growth. And the picture on the right shows a dendrite growing on a component under conformal coating, which is just an unusual thing. A lot of people think I don't have to clean because I don't have to worry about dendritic growth or cleaning because I'm going to coat. And as long as I coat it, everything is fine. Well, that's not true. So dendritic growth requires three elements. It requires conductive residues, electrical current, and moisture. Where calf requires four elements, all of these three plus a pathway. On the surface of the board, it is all pathway. It doesn't have to rely on a small crack. It travels over the surface of the board, so the entire surface of the assembly is a pathway. So conductive residues, electrical current, and moisture are the three elements required for dendritic growth. Now let's look at their process again and what part of their process contributed to dendritic growth. They cleaned with water, no chemical additive. I'll explain why that's an issue in a moment. They hand soldered with no clean flux, and they didn't clean it. And I'll explain why that was an issue in this case in a moment. No bakeout, which I've already described, and no knowledge of specific ECM-related failing mechanisms, which I already described. Had they had that knowledge, they may have looked at some of the above processes a little bit more critically. So they cleaned with water with no chemical additive. What's wrong with that? Well, there's several substances on a board that are undesirable to be left on a board, and these residue species fall into two categories. They're either polar or non-polar. Polar is hydrophilic, which means it loves water. Anything that is polar can be removed with just water, no chemicals necessary. Well, that makes sense. That made sense for this contract manufacturer because they were reflowing the boards with water-soluble paste. Water-soluble paste is soluble. It's polar. It's soluble in water. So in their world, they didn't need to run a chemical because they're only removing water-soluble flux. Well, the problem they had, like many, many, many assemblers have, is they have a mindset that when they're cleaning boards, they're running a defluxing process. Well, in actuality, they're running a cleaning process. Flux is only one of the contaminant species they're removing. In reality, they're really removing, or should be removing, many other forms of contaminant species. There are many other contaminant species on the board that are non-polar. They are hydrophobic. They are not soluble in water. And if a board is only cleaned with water, at best, it'll remove the polar substances, but it will completely ignore and leave behind all the non-polar hydrophobic substances. So flux is the one contaminant species we intentionally deposit onto a circuit assembly in order to reflow it. And that's what we intend to remove. But in addition to flux, there are a host of assembly-related residues. There are human-related residues. There are component fabrication residues, and there are board fabrication residues. I like to call all these the usual suspects because they are present on every circuit assembly made. Board fabrication residues include etch residues, developer chemicals, hassle fluids, alkaline cleaners, and more. Component fabrication residues include plating bath residues, mold release agents from the component reels, some silicone mold release that gets onto components, pre-plating, oxide cleaning, pre-tinning flux residues, water quality rinses, etc. All can stow away onto the circuit assembly from the component fabrication part of the business. And then assembly process residues. That's where we intentionally add contamination. We add flux from solder paste, from wave, from cord solder. We have cleaning chemical residues, water rinse quality residues, rework residues that we have on a circuit assembly. And then we have the human component. So we have what I like to call the Dorito effect. After lunch and breaks, boards tend to get a little bit dirtier, particularly when gloves aren't worn or finger cots aren't worn. Hand sanitizers, moisturizers, hand creams, things like that, they tend to make their way onto circuit assemblies, and many of these are non-polar. They are not soluble in water. So the flux residue is really just the icing on the cake. All boards are subject to board fabrication residues, component fabrication residues, assembly residues, human residues. And as I said, flux is just the icing on the cake. And when water alone is used to remove these residues, they don't. It only removes the water-soluble materials, not the non-water-soluble materials. Now, the other thing they did, which is not uncommon, is they reflowed or they actually hand soldered a through-hole component, and they used no clean flux in the process. That's not unusual. And the way they deposited the flux on this particular component array, unfortunately, is not unusual either. They used a little syringe, a flux dispenser, and they basically went from left to right with constant pressure on the dispenser and oozed out flux across this pin array. And they put a lot of flux on there, but in their mind, it's no clean. Who cares? It doesn't have to come off anyway. After the flux is oozed on from left to right, the hand soldering process solders in very small specific areas and properly activates the flux residues and properly encapsulates all the activators and oxidize agents and things like that, and does its job. The problem is when too much flux is put on and the soldering iron doesn't properly activate that excessive flux, as in this case, it leaves a lot of unactivated flux on the surface of the assembly. And that is extremely problematic because unactivated flux leaves activators and other bad actors, which create the conductive corrosive residue that can result in dendritic growth. What the soldering operator should have done was only apply flux to areas directly where the heat from the iron was going to be applied. And that would have ensured that all of the flux on the board was properly activated. It would act as an encapsulant for all of the activators and oxidation, and would protect the board from the possibility of dendritic growth due to the conductive corrosive surfaces. The operator should have, in most cases, not all, in most cases, they should have used flux cord wire, which they probably did, but they felt the need to add excessive flux to that. In many cases, flux cord wire provides all the flux that's necessary. If it's a very large component, then more flux would have to be added. Just make sure that the flux is only added to the areas where the heat is going to be applied. The reflow heat is going to be applied. Otherwise, it's going to be problematic later. They had no bakeout process, which also, as I said earlier, was problematic because it takes moisture along with the conductive corrosive surfaces and electrical current to grow a dendrite. They had no bakeout process. As I said earlier, the boards were allowed to pick up moisture during the time from fabrication to assembly, and including the several days they spent over an ocean. Also, the boards were clean. They were cleaned with water. They were cleaned in an inline cleaner, which is a fine technology. They used an air knife to remove the water from the surface. Air knives don't heat the board generally. They generally mechanically remove the water off the surface, and any water that picked up into the layers of the board was not removed because there was no bakeout process. So that was problematic. So what happened? They had electrical shorts created by dendritic growth. They had parasitic electrical leakage, and they had corrosion, which were major issues in this case. So when conductive residues, electrical current, and moisture combine, and the conductive residues were as a result of the usual suspect, the stowaway residues that were not removed from the assemblies because the cleaning process had no way to remove them because it was a water-only process, and a lot of the residues left behind were not water soluble. That caused a problem. There was also evidence when boards were analyzed, pulled out of the ground, and removed from their potting and analyzed. There was also significant evidence of corrosion. Again, another moisture issue. So almost to their credit, it was false logic, but almost to their credit, I can see where they came to this conclusion. They didn't need to do a lot of cleaning. They didn't need to worry about stuff because they're going to pot it. They're going to protect the board from environmental attacks, which they did that pretty well. The problem was when they potted the board, they basically created this sarcophagus where they intended to protect the board from outside attacks. They really trapped the sins of the process inside the board. So any moisture could not outgas, it couldn't escape. They created this little biodome of problems that could not escape. And that sealed the fate, not only sealed the board, it sealed the fate of the entire assembly. So they had recommendations. They had experts of various types from their contract conformal coating people and others that in writing, they said, look, you really need to clean these before potting. They didn't feel comfortable potting without cleaning, but they were told do it anyway. And they said, we really need to bake before potting. That's best practice. And they were basically, they basically rejected those recommendations and potted without cleaning, potted without baking. Why would they do that? Well, the VCs were saying ship. The VCs wanted to see, the venture capitalists wanted to see return on their money. And we have emails and documentation of these email threads that were really putting pressure on the contract manufacturer to ship these products, even though they weren't following best practices in order to make the shipping deadlines. It was just a classic case of we don't have time to do it right, but we'll have time to do it over. So the venture capitalists pushed for increased production and shipments. Improper cleaning left conductive residues behind. CAF-resistant board materials were not used. IPC CAF testing standards were never considered. Excessive flux residues allowed to remain on the assembly. Moisture allowed to remain in and on the board. Rejected advice from contract manufacturers and experts, and thousands of units were recalled, resulting in a multi-million-dollar lawsuit with hundreds of thousands of dollars spent in attorney's fees on both sides, the contract manufacturer and the OEM, because they were suing each other. So what do we learn from all of this? Well, number one, we learn to speak up. If your customer asks you to do something which is not best practice, which you know may not be the best for the product, say no now or speak up now, because it will ultimately land on your lap. Listen to the experts. This day and age, there are very few companies have cleaning experts, contamination experts. Seek out, like you're doing now, listen to the experts and get that advice and incorporate that into your best practice processes. Seek and adopt best practices. They're called best practices for a reason. And consult standards. IPC has a plethora of standards, including this CAF testing standard. Know your product. That's the big one. Know your product. And what do I mean by know your product? Know what its cost of failure is. And I for those of you who have been on my webinars before, you've seen this. I still love to show this. I mean, every product has a cost of failure. And this electronic flea collar has a defined cost of failure. This artificial pacemaker, this implantable defib device, has a cost of failure. What's the cost of failure in a electronic flea collar? It's an itchy dog. So one can agree it's a low cost of failure. What's the cost of failure in a cardiac pacemaker? Maybe a trip in one of these or worse. So should you clean a flea collar? Well, maybe not, because it's not supposed to last a long time anyway, and the cost of failure probably won't lead to major lawsuits. But you certainly want to clean or reduce the chance of failure. of a cardiac pacemaker because the cost of failure is high and the liability associated with that is very high. Know your residue tolerance. Every assembly has a tolerance for residue. If your product is going into an Amazon server farm where the humidity levels and the temperature levels are well controlled, it arguably can tolerate more residue than a board compared to a board going on an oil platform or a downhole or a medical device or an unpressurized part of an aircraft. Those would have a lower residue tolerance because they're in a harsher environment. They're going to be subjected to more moisture being one of the three pillars of ECM. Look at your component spacing. If it's a through-hole assembly with lots of space between cathodes and anodes, it arguably has a higher residue tolerance than a circuit assembly that's comprised of surface mount components, high density, very small gaps between cathodes and anodes. That assembly would have a much lower residue tolerance. Best practice would be remove the conductive residues. If you remove conductive residues, you won't have an ECM issue, period. At least a dendritic growth issue. You can still have calf. There are other best practice methods to avoid calf, which is baking materials. But the most common ECM failure is on the surface. That's dendritic growth or parasitic leakage. And that can totally be eliminated by removing the conductive residues that grow them. Rethink cleanliness standards. IPC is doing that for us. We're finally getting rid of the 10 micrograms of sodium equivalent per square inch or 1.56 per centimeter squared that ROSE testing provides. And we're going to a more defined test, one that requires secondary proof, basically, that whatever number you choose produces reliable boards. That's a long time coming. We're very pleased to see that. We've been proponents of that for quite some time. The old ROSE test standards that determine pass or fail were designed when this Jaguar was sold brand new for $6,800. That's when those standards came out in the 70s. So they're obsolete, and thankfully they're being reconsidered now. Remove and prevent moisture. Bake your boards before they go into production. After assembly would be the best time to do it. Keep the laminate boards in a dry box. Use first in, first out inventory control methods just to make sure that boards are going out as free from moisture as possible. Specify materials suitable for reliability expectations. Know where your product's going. If they're going to harsh environments, use better materials. And cleaning boards, since cleaning is the removal of contamination is the most effective way to eliminate dendritic growth. Just know that cleaning is not like horseshoes. It's not as close to the pin as you can get. It's all or nothing. We have to clean. You have to clean right. Otherwise, you can actually make the boards worse. But keep calm. Do it right. It's not that difficult. And just an easy 5-step process to cleaning, regardless of the type of cleaning machine you have, batch, inline, even manual cleaning. They all follow a similar process. In the case of batch cleaning, boards are loaded. In some cases, the serial numbers can be scanned for SPC purposes. Then they're loaded into the chamber. They're washed. The wash process solubilizes the residue, places them in solution. Then they're rinsed, where we replace the solubilized residues that are floating in the wash solution, and we exchange that with pure deionized water. We run through a cleanliness verification process to ensure that no wash solution, which has all the contaminants in solution, is left on the assembly. Is this a ROSE test? Is testing for cleanliness during a rinse cycle of a cleaning process a ROSE test? Well, the answer is no. No, it's not. It's not a ROSE test, no matter what anyone says. It's not a ROSE test. ROSE tests are defined by IPC, test method 650, 2.3.25. That defines what a ROSE test is. And ROSE tests require alcohol and water to be mixed together, 75-25 or at least 50-50, because on a ROSE test, we have to detect all contamination species. The rinse process of a cleaning cycle only uses water because we rinse with water. We don't rinse with chemical. And water is not capable, as I said earlier, of detecting all the usual suspects. It cannot detect anything that is not soluble in water. So any hydrophobic materials, any non-polar materials are not going to be detected during the cleaning process, during the rinsing process. Any machine that performs a cleanliness test. It's an extremely valuable process monitoring tool, process control tool, but it's not an actual cleanliness test because you're cleaning 20, 30, 40, 50 boards at a time. And if it says your board's clean, it says they're all clean, but it doesn't really know if they're all clean. It just knows that there's an average number. And that average number is good for process control. It's not good to say that that one board in the back left of the basket is the clean one and or the dirty one and the rest are clean. It doesn't know the difference. So it's a very averaged result. So just keep that in mind. It's not really a rows test. It's just a very good process development tool.
And then the final step is dry. So we load the boards, scan the barcodes, wash, rinse, verify cleanliness, and dry. Consider all the residue species that are going to be removed. As I said earlier, residue species fall under both soluble in water and not soluble in water, polar and nonpolar. The use of a chemical additive will allow the removal of all species of contamination. Besides being able to remove both polar and nonpolar contaminant species, there are other advantages of using a defluxing chemical additive in the cleaning process. One of them is that it contains anti-foaming agents. Sometimes the cleaning process generates foam based on some of the flux residues and other residues mixing with the water, and particularly in an agitated state. So anti-foaming agents come in quite handy for most cleaning processes. Also, defluxing chemicals contain corrosion inhibition agents, which protect the solder joints from becoming dull as a result of being in contact with a higher pH cleaning solution. The cleaning additives lower the surface tension, which allow, particularly during the wash cycle, that allows better and more easy penetration or impingement under low standoff components, which is very helpful in the solubilization process that takes place during the wash cycle. And keep in mind, another reason to consider a chemical additive is that 78% of all fluxes used today are not soluble in water. That's just a fact. All no-cleans are not soluble in water. Rosin fluxes are not soluble in water. And unless one is running only a water-soluble flux, and unless someone is convinced that there are no non-polar residue species on the assembly, which would be unlikely, one should really consider the use of a chemical additive in the wash cycle just to make sure every possible contaminant species is removed during the wash cycle. And even if the flux is soluble in water, as I just said, the usual suspects, all the other contaminant stowaway residues may not be. Let's also agree that this isn't cleaning. This is really dilution. It's just taking a concentrated contaminant or a contaminant concentrated on a certain part of the board and spreading it out. It's not usually a really good cleaning process unless it's followed up by a rigorous rinse where all of the spread out solubilized contamination can be removed from the assembly. Generally, it's just a dilution process, so it's not really cleaning. Finally, to wrap things up, here's some things that everyone should do. Know your product very well. Know its residue tolerance. Know its end-use climactic environment, which affects its residue tolerance. Know its cost of failure. Is it an itchy dog? Is it a trip in an ambulance? Is it anywhere in between? Know how clean is clean enough. The new IPC standards are allowing a variety of cleanliness testing methods and rows test scores, if you will, as long as you can prove that that score is reliable on your product. Know how to control the entire cleaning process. Just be in control of the process. And that will severely reduce and more likely completely eliminate any chance of electrochemical migration on the surface of the assembly. And one of my favorite anecdotes, and I end most of my presentations with this story. This is a real story. This is one of our customers that manufactures commercial grade, professional grade amplifiers and other types of products for the music industry. And as they transitioned from tube components, vacuum tubes, to through-hole components to surface mount components, they lost something. They lost the quality of their sound, and they couldn't really figure out why. And one day, one of their engineers thought, well, maybe it has something to do with cleanliness. Maybe the boards are dirty. They really didn't even need to clean their boards in the old days, because in the old days, it was all rosin flux, which was mildly activated, and the components were all through hole, and they were very far apart. And there really wasn't a ECM issue or a temporary electrical leakage issue associated with that type of technology. But suddenly they started having problems with the quality of their sound, and they sent us some of their boards, and we cleaned them, and then we offered to perform a variety of cleanliness tests. One of the tests would be rose testing. We could send it out for ion chromatography, visual testing, etc. And they declined all of our offers to test the boards, much to our surprise. And they said they have their own way of testing boards for cleanliness, and that was to plug the board in and connect a bunch of guitars to it and have a jam session in their recording studio. And they could tell what the sound of clean was. So I was quite impressed with that. Sometimes our cleanliness assessment methods can go out of the box and go to a real practical test. And in their case, they determined what their sound of clean was. So I'll leave you with this. Determine what your sound of clean is. What makes sense in your industry for your boards in the climactic environment that they're going to go into with their unique cost of failure. Know what your sound of clean is. So in the world of risk, this is all about risk. And risk management. We have several choices. We can reduce the risk by adding mitigating factors to our assembly process. We can transfer the risk, which is what we tend to do when we outsource products. If we're an OEM and we send our products to contract manufacturers, we kind of just transfer the risk to them. And that was a case in point in SMT wars. The contract manufacturer assumed all the risk and very little of the rewards associated with this particular project. We can accept the risk. We can just say, yeah, that's just part of the process. There's money in the product, so we could support the associated risk, or we can avoid the risk. And my point is to avoid the risk in this particular context. Simply remove the residues. If this particular contract manufacturer had just removed the residues and the moisture, in the case of calf, they would not have been involved in this very expensive litigation process. So if you have a salesman, if you're a contract manufacturing company and you have a salesman like this guy, whose mantra is, I can't say no, just reconsider whether that is a smart way to conduct your business. Don't give in to the temptation. Sometimes the word no is far more profitable than the word yes.
Well, that's another episode. Thanks for listening to Reliability Matters. If you like what you hear, please be sure to give us a like. Just click the like or heart button below. If there are any reliability-based questions you'd like to have answered or specific topics discussed, let me know. I can be reached at mike@mikekonrad.com. That's Konrad with a K. Don't miss another episode. Subscribe to Reliability Matters on iTunes or follow us on Spotify. You can also listen to us on iTunes, Spotify, aqueoustech.com, PCBchat.com, Spreaker.com, or our newest affiliate, Ascendo Reliability, on reliability.fm, a site dedicated to all things reliability. Once again, thanks for listening. We'll be back soon with another episode of Reliability Matters. In the meantime, keep doing it right.
Thanks for listening to the Reliability Matters podcast. Join us on the second and fourth Tuesday of each month for new episodes of Reliability Matters.